All right, so we're going to finish off this trig package that we started last week and then go through your trig exam. Remember, today at lunch is your opportunity for the Unit 3 rewrite if you've got your assignment complete. And then Wednesday will be Unit 2, the trig, right? So those that weren't able to make it on Saturday for the review session, it was recorded and posted on Google Classroom. So we went through the Unit 1 review package that was over on the counter. So we went through that. And then we also went through an extra package, this one here. We went through this as well. So that is also posted on Google Classroom. So if you wanted to pick this up, if you weren't here, couldn't make it on Saturday, you want to pick that up and go through it, you can follow along on the link on Google Classroom. And I also handed out this package of released items from 2016 with the solutions. So you could pick that up as well if you wanted to. So I said this before, this exam is not going to be easy. It's going to be, I believe, the hardest diploma exam that you will write. So you cannot afford to waste time. Use the time, prepare to the best of your ability. I believe after it's done, all said and done, that probably 95% of you will have regrets. You wished you would have studied more. You wished you would have spent more time preparing. Because it's not going to be easy. You got to know your stuff if you want to do well. If you know your basic stuff, you should pass. But if you want to do well, you got to know your stuff. So don't waste the time. Prepare. Put everything you got into it. Okay? You won't be sorry. So let's finish off this package. Find the general solutions. Remember, the general solutions means that the domain is from negative infinity to positive infinity. This is where we use multiples of the period for the function. So the general solution to sine 2 theta minus cos theta equals 0. Normally we solve trig equations by factoring, normally. Right? So we're looking for common factors. Sometimes we're factoring trinomials by getting two binomial factors. But in order to do that, you want to have the terms all in terms of the same trig function. And right now we have two different, sine and cosine. But sine 2 theta, if you look on the formula sheet, is 2 sine theta cos theta. That's right on the formula sheet. Don't have to memorize that. That's what sine 2 theta equals. And so by making that substitution, now you can take out a common factor of cos theta on the left. Remember, normally we solve equations normally by factoring. In some cases, if the equation has only one term with the trig function, you can get that trig function by itself by doing algebra. But in most cases, we factored. And common factoring we always looked for first, and if that didn't work, if we had a trinomial, then we tried to factor to two binomial factors. But once you have it factored, then the solutions will come when each factor equals 0. And for that second one, that'll be where the sine of theta equals 1/2. So our general solutions come from first finding the solutions between 0 and 2 pi. On the unit circle, let's start with the coordinates at each axis. So here it is 1, 0, 0, 1, negative 1, 0, 0, negative 1. Remember that the cosine is the first number in the ordered pair. And so the cosine equals 0 up here at pi on 2 and down here at 3 pi on 2. If you were looking for solutions between 0 and 2 pi, that'd be your answers. But we're looking for the general solutions. And in this case here, we can write in terms of one statement. And that would be that theta would equal pi on 2 plus n pi. If you add a multiple of pi radians, which is halfway around the circle, from pi on 2, you would end up at 3 pi on 2. And if you did another multiple, yes. Okay, so we'll do that. Thank you. So it'll be 90 degrees plus 180 n degrees. So again, if you start at 90 and you go 180 degrees, which is halfway around the circle, you'll end up at 270, which is the other place where cosine is 0. And if you do another 180, you're back up at the top. You can also do this in a negative direction. So that's where we use, at the end, we'll say n is an element of integers, because that will cover all positive direction angles and negative direction angles. I'm going to move that over a little bit because I need some more room for the next part. The next part comes where the sine of theta is 1/2. So if we start building the first quadrant of the unit circle, that first stop is pi on 6. And the coordinates there are root 3 over 2, comma, 1/2. And that is where the sine is 1/2, because sine is the second number on the unit circle at the coordinates. And so pi on 6 is one answer. And from there, we would have to add one full revolution of the circle. And again, I did it. I'm supposed to be in degrees, so let's fix that. So that would be 30 degrees plus 360 n degrees. And then the other place where the sine is also positive 1/2 would also have a reference angle of 30 degrees, which is 150 degrees, 30 degrees short of 180. So this will be 150 degrees plus 360 n degrees. So there are the general solutions to that equation. Number 25, 3 students were given the identity there. Student A substituted theta equals pi on 3 into both sides of the equation and found that the left side equaled the right side. Student B entered the left side into y1, right side into y2, concluded that the graphs are exactly the same. Explain why these methods are not considered a proof of the identity. So we did these methods as a check, okay? But we also talked about the fact that these first two methods wasn't sufficient to proving an identity. So student A only showed that it was true for one specific angle. So student A showed that left side equals right side for one specific angle. Not all angles. Not all possible angles. So that's why that is not sufficient for a sufficient way of proving an identity. Student B showed that left side equals right side for whatever domain the calculator is set for. And when we say domain, we're talking about those windows, the X min and X max. That's what we're talking about. Once again, not all possible angles. Only for certain angles, whatever windows are being used. Student C correctly completed an algebraic process to show that left side equals right side. So show a process that student C might have used. So this is the algebraic approach that we did. So we'll start with sine squared theta minus 1 all over cos theta has to equal negative cosine theta. So on the left side, normally we worked down the part that was more complicated to make it simplify it down to what the right side is. And so on the left side, I can work with that sine squared theta minus 1. And this comes from the Pythagorean identity. This is on the formula sheet. Sine squared theta plus cos squared theta equals 1. So if you subtract sine squared theta from both sides, you'll get cos squared theta equals 1 minus sine squared theta. So that's a process that we did quite frequently. We use that Pythagorean identity as well as different variations of it. Now, on the right side, it says 1 minus sine squared theta, which is actually the opposite of sine squared theta minus 1. Because here, the sine squared theta is positive, over here it's negative. Here, the 1 is negative, over here it's positive. But if we multiply both sides by negative 1 here, we'll get negative cos squared theta equaling negative 1 plus sine squared theta, which is the same thing as sine squared theta minus 1. So sine squared theta minus 1 is the same as negative cos squared theta over cos theta, which is negative cos theta. We didn't even need the other part. It's actually done in two very straightforward steps. Remember though, at the end, when you are done, you need to say left side equals right side. Talked about the fact that that tombstone symbol, which is just a box that's colored in, means the same thing. That means that you proved what you were required to prove. But if you get a trig proof on the diploma exam, you must have something at the end to say you did it. If you don't, then you would lose half a mark, assuming everything else is correct. So you don't want to do that. Just throw marks away. Now we're asked for the non-permissive values. Well, the only place where we have a denominator here is cosine theta on the left. Cosine theta cannot equal 0. And if we go up at the top, we see that the cosine equals 0 at pi on 2 and 3 pi on 2. And in this case here, it doesn't tell you whether to use radians or degrees, so I'm just going to choose to use radians. So theta cannot equal pi on 2 plus n pi, where n is an element of integers. So there are the restrictions. Number 26. What is that equivalent to? So again, basically we're doing the same thing that we just did. We're going to simplify an expression. And you might remember that we had some hints that we used. The first being that if there's any powers, look to those Pythagorean identities, especially if there's squareds in them. If there's higher powers, we factor. But if there are no powers, we put everything in terms of sine and cos. So that's what I would do here. The first term, cotan, which is cos x over sine x, plus cosecant, which is 1 over sine x. And that is all divided by secant x, which is 1 over cos x plus 1. So I've got addition, division, and then addition. To do the addition parts, we need common denominators. This first section does have a common denominator of sine x. So it'll be cos x plus 1 all over sine x. But for the second part, we need a common denominator of cos x. So we would make 1 equal to cos x over cos x. So this will be 1 plus cos x all over cos x. And if we look back at what our four choices are, right, you can see that you need to break this down into a single term. To divide fractions, we multiply by the reciprocal, so that would be my next step. And then the cos x plus 1 and the 1 plus cos x are the same thing. Same two terms. They're all positive, so they cancel. And we are left with cos over sine, which equals cotan x. And that's why D is the correct answer. Now, if you got a question like this on the diploma exam, you could actually do it by graphing the original expression and then graphing the four answers that are given and see which graph matches. Which of those four graphs matches the original, right? You could also, even if this was a written response question, you could use your graphing calculator to make sure that the answer you got at the end is equivalent to what you started with by, again, graphing both and making sure that the two graphs were the same. So this next question, each trig expression can be simplified to a single numerical value. So when they are written in simplified expressions and arranged in ascending orders, the expression numbers are what? So we want to get the numerical value for each one and then order the four expressions in ascending order. So that's from lowest to highest value. So the first one is cotan squared x minus cosecant squared x. So let's do this below here. We've got cotan squared x minus cosecant squared x. If you look on the formula sheet, you will see that cosecant squared x is 1 plus cotan squared x. That's on the formula sheet. That cosecant squared x is equal to 1 plus cotan squared x. It probably says 1 plus cotan squared x equals cosecant, but that's the same thing. But remember, we're subtracting all of the cosecant squared x, so we're subtracting all of the 1 plus cotan squared x, which means it's in brackets. And a negative sign in front of the bracket changes all the signs inside. The cotan squared x's cancel, and you're left with a value of negative 1. So that's the value of that first expression. The second expression is secant squared x minus tan squared x. If you look on the formula sheet, you will see that secant squared x is equivalent to 1 plus tan squared x. That will cancel with the minus tan squared x, and you're left with positive 1. That's the value of expression 2. Expression 3 says sine x minus tan x over secant x. So we need to simplify this. And we can do that by working with that second term, tangent, which is sine over cos, divided by secant, which is 1 over cos. To divide by a fraction, we multiply by the reciprocal, and then the cosine x's will cancel, and you're left with sine x minus sine x, which is 0. That's the value of that expression. So now we need to do the last expression, 1/7 cos squared x plus 1/7 sine squared x. There is a common denominator there of 1/7 that could be taken out. And then you'll have cos squared x plus sine squared x, which from the Pythagorean identity is 1. So it's 1/7 times 1, which is 1/7. So if we're going to order these expressions from lowest value to highest value, that's ascending order. The smallest one is the first expression. Its value is -1. The next smallest one will be the third expression. Its value is 0. Then the last expression, because its value is positive 1/7. And then the second expression has the highest value of positive 1. Number 28. Normally, the exact value means you're using the unit circle. The problem is that 75 degrees is not on the unit circle. So we did these by finding two angles, in this case, that add together to get 75, and both of those are on the unit circle. So 45 and 30 degrees will work. So we would use the sum identity for tangent that's on the formula sheet. And that is tan of A plus the tan of B all over 1 minus tan A times tan B. The tan of 45 is 1, plus the tan of 30 is root 3 over 3. Just getting that from the unit circle. All over 1 minus the product of 1 and root 3 over 3. So this gives us 1 plus root 3 over 3 all over 1 minus root 3 over 3. We can't cancel anything because you can't cancel parts of binomials. But to simplify this, I would first start by multiplying all the terms by 3 because that'll get rid of my denominators in the numerator and denominator. The first term times 3 will be 3 plus, when I multiply the second term on top by 3, they cancel, and you're left with root 3. Same thing on the bottom. It'll be 3 minus root 3. And now, we get rid of the radical in the denominator by multiplying by the conjugate of the denominator. That's 3 plus root 3. So, on top, 3 times 3 is 9. The outer product will be 3 root 3. The inner product will also be 3 root 3. And the last, positive times a positive is a positive, and root 3 times root 3 is 3. On the bottom, 3 times 3 is 9. Here, the outer and inner products cancel. This will give us 12 plus 6 root 3 all over 6. And now we can divide everything by 6, and we'll get 2 plus root 3. All three terms are divisible by 6, so we can do that. It'll be 2 plus root 3 over 1. And you could check this on the calculator in degree mode. Take the tangent of 75 degrees. It's that decimal. So that should equal 2 plus the root of 3, the answer we got. And it does. So that tells us that the answer is correct. All right. Number 29, again, we're asked to prove this trig identity. So, in this case, we're probably going to have to work down both sides. Looking at the right side, and it's actually not as bad as it looks, but looking at the right side, cos squared x minus sine squared x on the bottom there. If you look on your formula sheet, that is one of the variations for cos 2x. Cos 2x, there are three different expressions that are given. One of them is cos squared x minus sine squared x. So this is going to be sine 2x over cos 2x. And sine divided by cos is tangent, so it'll be tan 2x. And if you actually look on the formula sheet what tan 2x equals, tan 2x is 2 tan x over 1 minus tan squared x. It's done. Look on the formula sheet to what tan 2x equals. It equals 2 tan x over 1 minus tan squared x. So again, left side equals right side. We've proven what we were told to prove. This could also be done by putting everything in terms of sine and cos. It would work. It would just take a few more steps. But it would work. This method, though, is much, much easier.